Hello, everyone, and thanks for joining the Lattice Developer Conference 2024. Today's subject is analyzing and optimizing lower power consumption in an FPGA. My name is Murad Zakama, an application engineer with Lattice. I have over 20 years of experience in semiconductor industry, mainly in FPGAs. My main area of expertise is Lattice hardware and software, as well as some design techniques and best practices. As for the academic background, I have a double E with a master's degree in microelectronics and an MBA from the University of Quebec in Canada. So what's the agenda for today? So we're going to start with a quick introduction of power consumption. So the different types of power consumption, whether static, dynamic, bias, and how we model this inside the FPGA. And then we'll move into the software side of things, where we look at the software available from Lattice, the Power Calculator, and its different mode of operation, whether estimation mode, calculation mode, and simulation mode, and what are the differences between all these different modes. Then we will move to native low power advantages. Lattice has been known for its leadership in the lower power space for small to mid-range FPGAs. So why is that, and what makes them very competitive in that space? And we'll cover some design techniques to optimize further the power consumption in an FPGA. Then we end up with a summary and frequently asked questions. So let's start with the power consumption theory. What is power? So I'm going to start with a very simple extract from Wikipedia to define power. So power is the amount of energy transferred or converted per unit of time. It is in the International System of Units. The unit of power is watt, so joules per second. So in an electrical circuit, so the power is defined as the voltage multiplied by the current. So the power at time t is the voltage at time t multiplied by the current at time t. And obviously the voltage is the potential difference or the voltage drop that we see across the circuit or the component. And the I is the current that is traveling through that component. So what does impact power? So there's mainly three main factors that impacts power. So temperature, capacitance, and activity factor. So temperature has an exponential effect on power. So power increases exponentially with temperature. We're going to see examples of that later on. The capacitance is the capacitance of the transistor. So the more logic you have, the more capacitance you have in your circuit, and charging and discharging that capacitance consume power. And obviously the process node will have an impact on that capacitance value and consequently on the power consumption. And finally, the activity factor, or the number of changes per clock cycle. So how many flip-flops, how many wires are changing status in each clock cycle, because that change in status translates into power consumption. And the higher the activity factor, the higher the power consumption will be. And we'll cover more in details each one of these later on in the presentation. So let's start with the impact of temperature on power. So we have an extract here from the Lattice Power Calculator with a graphical representation of the exponential effect of temperature on the power consumption. As you can see in this graph, in the x-axis we have the temperature, and in the y we have the power consumed by this specific design that we ran through the power calculator. So at 17 degrees, we have a 14 milliwatt consumed by the device. If we increase the ambient temperature to 68 degrees, then that power consumption more than double. And to modelize this behavior in an equation, this power consumed by the FPGA is corresponding to a static power, actually, that we're going to see in the next slide, but it's modelized by this equation. So A is a coefficient multiplied by exponential, B another coefficient, and the temperature value. And these coefficient that you see here and more coefficient that we're going to see in next slides are calibrated with hardware behavior. So after we design the chip and we get the hardware back, we calibrate this coefficient to be aligned with the hardware behavior. So power has three components. So we talked about static power in the previous slide. And that static power is exponentially proportional to temperature. So what is static power? Static power is related to the leakage current that you have inside the FPGA. It's basically a programmed FPGA with a bit stream, but with no activity in it. And that portion of the power called static power, and that is represented in this component in the equation. Bias power, on the other hand, is related to voltage applied to the substrate and is independent of temperature, and that's a constant. And then dynamic power is related to the activity of the design. So the dynamic power is proportional, linearly proportional to the frequency. The higher frequency you have, the higher switching in your design, the higher the power will be. So the total power will be the sum of all these different components multiplied by the voltage. Obviously, this is a simple equation here, but in the FPGA, things are a little bit more complex because there may be multiple voltages within the FPGA, multiple components, and the calculation of the total power is more complex than a simple equation. The nice thing is the power calculator offered the required interfaces and tools to do this calculation for you without getting into the details of it. So when we talk about power, so when you have power dissipation by the device, it has to be transferred, that heat that is generated has to be transferred to out of the chip. And when we get to that dissipation behavior, we talk about thermal resistance. And the thermal resistance defines how well the material is good to dissipate power. It is measured in degree per watt. And there is different thermal resistance that you can find in the documentation. And these are also characterized when we characterize the device. There is the theta JC, which is the thermal resistance junction to case. So that's the silicon to the case thermal resistance. If you have a heatsink, you can have a thermal resistance related to the case to heatsink. Same thing for the board, junction to board, thermal dissipation. The board size has an impact also on how well the power or the heat get dissipated from the device. The case to temperature and junction to temperature, and actually junction to ambient is the addition of the thermal resistance for junction to case and case to ambient. So why do we need to know all these parameters? These thermal resistance will allow us to calculate the junction temperature. So how hot is the silicon inside the device is getting. And we need to make sure that that silicon doesn't get outside of the specification for what it is designed, whether for commercial, automotive, industrial specs. So we calculate the junction temperature by adding the ambient temperature with the junction to ambient thermal resistance multiplied by the power if we are using the ambient temperature as the base of our calculation. We can calculate that also if you have information about the case temperature with the junction to case multiplied by power plus the temperature of the case. That will also give us the junction temperature. And same thing for the board. So there's multiple ways of calculating this, and the tool actually allow you even to estimate these different thermal resistance and have a calculated value or effective theta junction to ambient, for instance, in degree per watt. If you define the board size, the board type, the heatsink, if there's any airflow, that will play a role also in terms of dissipation of the heat. And once you define all these variables, the tool, power calculator tool, will provide an effective theta. So where does this terminal profile get defined? So if you open the Power Calculator tool, you're going to get a terminal profile option that you see here. If you click on this, there will be this pop-up window that will provide the option either to have an effective data calculated by the tool. If you have your own tool to estimate the terminal resistance of your system, you can enter that by using this option. So once you enter this option, this window will get out of will not be grayed out, and you'll be able to enter your effective data. So we provide the thermal resistance, we provide the ambient temperature. So what do we get out of the tool other than the power consumption? We get the junction temperature and the maximum safe ambient temperature. And these will provide you with information of how hot is the device, or what ambient temperature you should not exceed to keep the device operating in its safe operating range. So that get us to this Power Calculator tool, and the Power Calculator tool has a different mode of operation. It has estimation mode, calculation mode, and simulation mode. We're gonna cover briefly each one of these modes in this presentation. You can scan the QR code, and that will get you to the full training associated with the Power Calculator available on Lattice Insights, and that will give you deeper, probably dive in each one of these modes and how to use them and the difference between each one of these modes. So how does the Power Calculator perform this calculation of the total power of the device? It's actually using the same equation that we've seen in the previous slides. So it applies this equation on each single functional block within the FPGA, taking in consideration the voltage at which it's running and the number of resources that are available, and will use the equation to calculate the current, then multiply that by the voltage of that sub block or that functional block, and that will provide us with the total power of the FPGA. So the Power Calculator need input to provide the power, the system power, or the FPGA power. And it has different mode of operation. So there's the estimation mode, which can be edited by the user. There's the calculation mode that take information from the output of the software. And there is the simulation mode that allow you to use simulation data to determine the activity factor. And we're going to go through these different modes in a little bit more details in the next couple of slides. So let's start with the estimation mode. So in the estimation mode, you can create a Power Calculator project and provide the tool with an estimate of the resources that you're going to be using. It could be, this mode could be used early in the design. You don't have a VHDL code. You don't have a design that you can run through the tool. So you want to know approximately what's the power consumption of your FPGA by providing the number of lookup tables, the number of clocks, the number of EBRs, DSPs that are used, and the tool will provide you with a rough estimate of the power consumption. So obviously, since all these inputs are not accurate, the output of the Power Calculator is not that accurate, and it's only used for rough estimation. So how about the calculation mode? So in calculation mode, the design, you're probably already in design phase. You have the VHDL ready or Verilog ready. You run through synthesis, you run through map, place and route, and you have this unified database which get generated by the tool that include every single details that you have in your design: the number of lookup tables, the number of EBRs, IOs, the routing resources. It's a true representation of what will be implemented in the FPGA. And that will be an input to the Power Calculator. Now we have a very true representation of our resource utilization. We can even include the frequency. So we know at what frequency our design would be running. So we use that to estimate the switching of our flip-flops inside the FPGA. The only variable that's still open at this point is the activity factor. So we have to estimate that, and statistically, usually it's between 10 and 20%. So obviously, this mode will offer a better power accuracy and provide you a very good estimate of your power consumption. The only variable that the user input is the activity factor. So there is another mode which get even a step further in terms of estimating the activity factor, which stays as the only component that is not well defined and as an input to the power calculator, and that's called simulation mode, or based on a VCD file. So the VCD file is actually a recording of all the transition that happen in simulation of your design, and based on that activity, the power calculator can extract an activity factor per block that it will use to calculate the overall power consumption of the device. Obviously, when you do this, it depends on the test bench. If your test bench is representative of the real operation of the design, that activity factor will be very accurate. If it is a corner case use case or a corner case test bench, then that information may not be that accurate. Just keep that in mind. So when using this simulation mode or advanced calculation mode, you get a very accurate power representation or power consumption representation from the power calculator tool. So we've seen how the power calculator works, the different mode of operation, and we talked about this activity factor. So what is activity factor? How do we determine this activity factor variable? So activity factor is defined as the average number of signal transitioning per second. A transition is defined as a signal moving from 0 to 1 or from 1 to 0. So all these involve capacitive load or charge and discharge, and it represents some power consumption. So in asynchronous logic, it's pretty straightforward to determine the activity factor if you know exactly how your design operates. We're going to take a simple example of a counter here to illustrate this concept of activity factor. Your design will be much more complex than this, but just to understand the concept of activity factor. So a 3-bit counter has an activity factor of 58%. How do we calculate that? So we take every bit of the counter, so we know bit 0 will be changing every clock cycle, so that's an activity factor of 100%. Bit 1 will have an activity factor of 50%, and bit 2 will have an activity factor of 25%. So if we average all these numbers together, we get the 58%. Just to put things in perspective, an 18-bit counter will have an activity factor of 11%. So that's relatively easy for a simple use case. For a design, you have a mix of multiple function, so estimating this activity factor becomes a little bit more complex. One thing to probably try to avoid when doing a design is having combinatorial logic. Combinatorial logic is hard to predict the activity factor for the simple reason that these any change in the input will immediately impact the output, and even if there's a glitch in these combinatorial logic, it may create some toggling, and that toggling is actually an activity factor, charging and discharging of some capacitance within the FPGA. In general, there is certain designs that are potentially high activity factor, like adders, forward error correction, Reed-Solomon encoders, decoders. These tend to consume a lot of switching activity factor, whereas others may be a lower activity factor. So control logic, power sequencing, they don't necessarily change often, and they have a lower activity factor. A real design will have a mix of multiple function. On average, these will be around 20 to 10% in terms of activity factor. The number of registers that are switching at the same clock cycle will represent 20% of the total number of registers. So we've seen what is an activity factor, and the fact that these variables stay as a rough estimate and depends on the design and how the design, what's the characteristic of the design. Obviously, this impacts the dynamic power. So having a rough or a wrong estimation of this activity factor would have an impact on the output of the power calculator. Usually you are pretty safe between 10 and 20% to have a very good representation of the activity factor and have a good accurate output from the power calculator. So Lattice has been known for being the leader in low power FPGAs for small and mid-range FPGA. How do they achieve that? How do we achieve that power advantage? This will be summarized in the next section. These factors that are related to the process node, to the architecture, and to the design techniques that are adopted to design every single piece of the or component within the FPGA. So for Nexus family, I think the most important criteria that allow us to have a very good power advantage is the FD-SOI technology, or fully depleted silicon on insulator. What you see on the right-hand side is the image of the transistor in silicon, and this is a traditional way of building the transistor with the channel, the gate, and source and drain. And in order to activate the channel, they have to apply some voltages on the gate to be able to activate that. So with the FD-SOI technology, there is an ultra-thin buried oxide layer on before the channel to make the channel smaller, and that will allow us to have a couple of advantages. So there will be significantly less leakage current associated with the transistor. The threshold to enable or disable the transistor will be much lower. There is also an impact on the temperature, so reduced temperature dependency when you use this type of technology, and very high reliability. We're going to see in the next slide that we can get up to 100 times better reliability or resistance to the SEU, single event upset, using the FD-SOI technology. The other nice thing about the FD-SOI is we can tune the device to be in high performance mode or low power mode, and that's only by applying some bias current on the substrate. And you will notice in the Lattice software tool that you have the exact same device. Let's say X05 NX that is offered in -9 low power and -9 high performance for the exact same ordering part number. So that's tunable through the software, not through ordering part number. So what are the competitive advantage of Nexus family? And the benchmarking of these devices has shown that we have up to 75% lower power than the same category of devices than Nexus, and better performance, so for video connectivity. So these devices being architected for the small density FPGA, we have the luxury of integrating also higher performance interface logic to be able to support higher speed SerDes or higher speed memory interfaces and so on. So we can offer up to 2x faster speed for video connectivity, and also a much smaller soft error rate, or more resilience into the soft error rate, with up to 100 times better, which impact obviously the reliability of the device. The other strategic decision that has been made by Lattice to stay in this low power leadership situation is to use Lat4. To implement logic within the FPGA, some of the competition or competitive FPGAs move to a Lat6 and other structures also